And so thank you for the introduction. I've been working with Isaac since 2016. And first, I would like to give credit to some of the folks who have worked out at Isaac. We got Isaac in 2014 so that we could do advanced manufacturing relevant to industry. These are some of the folks that have worked with us over the years. And in fact, there are new people that I haven't actually even added to the list, since this is the list that was current as of March. But let me start with some fundamentals for those who are students, interns, and for those who it's been a long time since they thought about actual structures. Then I'll talk about some of the background of Isaac and then some of the projects that we have worked in our capabilities. So the first question is, what are structural composites? So a composite is anything that is made from multiple kinds of materials. Examples are wood. It has a fiber and it has a resin. And another example is carbon epoxy. So wood is what the first airplanes were made of. That's what the Wright brothers used. Then the industry moved to aluminum, and now we're using largely carbon epoxy or graphite epoxy. And so we've kind of come full circle in that regard. Fiberglass is another composite that is quite popular in the boating industry. Problem is it tends to be kind of heavy, doesn't matter as much for boats, matters a lot for airplanes. Some of the characteristics of types of composites we use are that they are typically layered structures, which means that you place one layer of material with your fiber and running in a particular direction, and then you place another layer of material. And so you build up your part in that manner. The other issue is that they are anisotropic, which means they don't have the same properties in every direction. When you talk about aluminum or other metals, you've got basically the same stiffness, the same strength, the same characteristics in all directions. Whereas with a typical composite that we use for aircraft or spacecraft, they have very different properties depending on what orientation you're looking at, which changes how you do your design and how you do your manufacturing. So what is the advantages of carbon epoxy compared to aluminum? Long history of building airplanes out of aluminum, worked great. So why in the last few years have we switched over to carbon epoxy? Well, first of all, carbon epoxy is lighter. If you just talk about specific density, it's a lighter material than aluminum. It's also stiffer than aluminum. So if you think about pound for pound, you have huge advantages there, because when you're building an airplane, weight is very important. It affects your fuel burn. It affects, therefore, the emissions that you're putting out. And if your plane is too heavy, it just isn't going to get off the ground. In the spacecraft world, weight is even more important, because every pound you have in your structure, every pound that you can take out of your structure is a pound you can put in your payload. And of course, pounds to orbit is hideously expensive. And so it's even more important to get your structure as light as you can in spacecraft. So the other advantage is that, as I mentioned, you have fibers which run in a particular direction. That gives you an opportunity to tailor your structure, which you can't do with aluminum. You want to set your fibers to run in the direction of your maximum load. And so if you've got a loading environment where it's not the same in all directions, which is usually the case, then you can design specifically to meet your loading requirements and have it weaker or less stiff in the direction that you don't have as high a load, and still meet your weight requirements. So that's a big advantage. When you talk about airplanes, you want your wings to be long and stiff and thin. You can't get there from here if you're going to go with aluminum. And so to get the kind of high aspect ratio wings that we want today, you've got to go to a composite structure. And I mentioned thin wings. Of course, that makes the aerodynamicists happy. You want higher lift, lower drag. So a lightweight thin wing is the perfect solution. The other advantage to going to carbon epoxy is the low coefficient of thermal expansion. That's less important in aircraft for the most part than it is for spacecraft or space structures, which are going to be sitting around either in orbit or on the lunar or Martian surface. If you think about the kind of temperature extremes that are experienced in, say, sitting at the polar region of the moon, many cycles. And that's where you want to avoid all the thermal effects associated with all those repeated cycles. And if you want to talk about a telescope, all those thermal cycles will totally mess up your pointing of the telescope. And so composites, carbon epoxy or carbon with another kind of resin are very useful for that kind of situation. And so this is Isaac. What you see here is the robot that's located in building 1232A. As I mentioned, we brought Isaac here in 2014, and we brought it here because it will do robotic manufacturing similar to the way that airplanes are made. That way, we have always been able to do design, analysis, and testing at Langley over our 100-plus-year history. But now we can also do fabrication in a manner similar to what is done at an industry. Electroimpact built our robot. They also build robots that build the 787. And so we have a direct connection to a manufacturer of real aircraft structure, which helps us understand the real issues and the real problems. Up until we got Isaac, we could build composite parts by hand, sure, but just because you can do something by hand doesn't mean you can scale it up and do it in the same way industry would. And therefore, it limited our ability to be able to try things out and do things that will eventually get onto airplanes. We could still do good research, but we had to partner with other people to do the manufacturing. And those of you who are familiar with working with the government, you know how things like that goes, particularly if as you're running through something, you decide you want to make a change. Well, if somebody else is building the part and you decide, oh, wait a minute, we want to change this a little bit, that could take weeks. It might require a contract modification. Not a fun, not a timely activity. With Isaac, we can build something, we can see it's not working. We have had a case where we had someone go home, reprogram that night, and we were back up and running the next day. You could never do that working with industry. And so that's why it's really valuable to have that in-house capability to be able to make those changes. We are a research center, and that's part of research. And so we want to look at aircraft and spacecraft. Our goal, of course, is lighter, safer, structurally optimized, meaning as light as possible to meet the loading requirements. Go from smaller scale, including little coupons, up to large scale structures. And I will show you some examples of the things we have built on Isaac. We're not trying to build whole airplanes. We're simply trying to build parts that are large enough to be relevant to support our aircraft and spacecraft programs. And we want to be able to transfer that information to industry quickly. If you're just building it by hand and you go to somebody in industry and say, hey, this is a great idea, you should try it, they're going to look at it and say, might be a great idea. How many years is it going to take me to develop it to the point where I can use it? Now I have to sell that idea to my CEO, my stockholders. I'm not going to get a benefit for years. Yeah, maybe not. But if we can actually demonstrate a capability, a potential on something that they consider relevant, like Isaac, then they are more likely to say, oh, yeah, maybe we could do that. And so that's why it's important for us to be working with industry to get the kinds of things that we do here out to get on real aircraft and spacecraft. So Isaac is a robotic system. I'm not going to read everything that's on the chart here. We have several joints. So Isaac can move like your arm can move, wrist elbow. And we can run on a 30-foot long carriage. And you can see here, we can run along here, and we can place material on our flat table, and we have our rotary table. Everything is computer programmed first, and then everything is computer controlled. The rotary table works like an old-fashioned turntable. And so once you program the robot, the rotary table is also programmed, and they will do a dance basically together to build your part if you're building on the table. As I mentioned, everything's computer controlled with the electro impact software system. That the software is written by a company called CG Tech. They allow us to do the programming. There is an inbuilt simulation system. So after you program, you can actually run a simulation and watch how Isaac moves on your computer. And it is tailored to our Isaac cell. So it knows where things are. So it will say, no, you can't do that because you're going to crash into something. But what we have learned is that it's not 100% accurate. There are things that the simulation will let you do that you really shouldn't, and vice versa. There are things that the robot might do that the simulation says won't work. And so, particularly because we're trying to push the limits, we're trying to do things that Boeing doesn't do. We've learned that we need to dry run every program, unless it's something very simple like a flat plate, just to make sure that the simulation, it does what the program said, and that in the real world, Isaac is going to do what the simulation says. And so we always run a dry run without any material, just to make sure everything works right. So we have two capabilities out at Isaac. First, I'm going to talk about automated fiber placement. The 787 is largely composite in their wings and fuselage, and that is state-of-the-art for aerospace. That is made with carbon epoxy, what we call pre-preg, which means it's got carbon fibers embedded in an epoxy resin system. And so when we place material with Isaac, using the automated fiber placement system, that's what we're placing. It's the carbon fibers in a tape that is placed a little bit at a time. And I'll show you a little bit more about that on the next chart, or a later chart. We also now have through thickness stitching, which is a up and coming capability, which we worked with Boeing to develop in the Environmental Responsible Aviation Program. That was a very successful program that ended in 2015. At the end of that program, we said, hey, we want to have that capability in-house. Why don't we build a robotic head that we could put onto Isaac so we can do through thickness stitching? The issue with composites is that layered material tends to be very weak in the thickness direction. And so what we're coming in here with through thickness stitching is putting threads through the thickness of the material to strengthen in that direction, instead of having to come in and drill holes and put in fasteners. And I'll talk about that in some later slides. So the Isaac head that you see here has 16 spools of material at most. This is a spool that would go on Isaac. Each individual toe that you see here is 1/4 of an inch wide. We can put 16 of these on the head at one time, and so we can place 4-inch wide swath of material at once. We can place a smaller number, and everything is programmed so the robot knows when to start placing a toe and when to stop placing that toe. We also have a smaller roller. Everything is placed. We've got a roller that comes over and compacts it down. But if you think about 4 inches wide going into a concave area, then that roller can't get all the way down. And so it's helpful to have a narrower roller, in this case 2 inches wide, where we can place less material, but we have a better chance at getting into that cavity. And so we use both of those systems. I'm not going to go into the details of laydown rates and things, but we're not trying to crank out airplanes the way Boeing is. So we don't have to go at the rate they're going. We just have to go fast enough to demonstrate the capability. We'll let them worry about getting to those next steps to place, full airplane wings. As I mentioned, we can place on our flat table and our rotator, and everything on the rotator has to move in time with the head itself. Non-destructive evaluation is very important to us. If you think about building an airplane wing, the last thing you want to happen is find out there's a problem with it after it's already built. And so NDI is very important. Typically what happens is the operator will go out and visually look at the part and say, oh, wait a minute, there's a problem right there. I need to replace that particular toe. Maybe the toe was defective. Maybe when it came out of the robot, it twisted. Those operators out at places like Boeing are really good at going out there, pulling up a toe, putting in a new one, and moving on. But it's all depends on the human seeing it and making the fix. If you've got an automated system which will flag the operator and say, wait a minute, there's a problem here, or a visual indication that shows, wait a minute, the colors are wrong here, then the operator knows there's a problem and will go out and fix it. The system that I'm showing here was actually developed at Langley and we have used the folks in the research director at NDI branch to help us with this. So they'll come out to Isaac, set up their system. They've got an infrared camera, and so they will track heat distribution. And what you see in the middle picture here is the bright area is heat. The next on the layer below what we're placing, the next layer, we're placing material on top of that. And ideally, there will be the same color, the same heat level through that whole bit. What you see here is you see that bright yellow coming through. That means that you've got a gap in the new material where you can see through to the old material. And that's where you have to look and say, well, does this matter? Is it big enough that we need to replace it? Or is it acceptable? And that's all a case-by-case basis. The other thing we can use this system on is after we have placed an entire layer of material, we can go back and determine whether or not there's trapped air or FOD caught in there. What if there's something in there that's causing the layer not to go down smoothly and therefore air was trapped? The bright light you see along the edges here, that all indicates trapped air. And we knew we were going to have trapped air, but this is a new capability, a new potential for tailoring parts, and we want to be able to understand that. And we can understand that a lot better if we can actually take something and look at it and try different things and see, well, what traps more air and what doesn't, and how do we get rid of that? And so that's where the NDI system's been very helpful. As I mentioned, with through thickness stitching, we actually have two stitching heads, one which is much like you might have a machine at home where you've got a needle and it goes up and down and does a straight seam. But of course, it's got to be a lot more heavy duty since now we're stitching through layers of carbon. In this case, it's dry fabric instead of the pre-preg material. There's no resin here yet, so it's just like floppy fabric. But it's still carbon rather than cotton that your shirt might be made out of. The thread also has to be different because thread needs to go through this system, and to make that thread strong enough to be useful after the part is completed, we want to have something better than your typical cotton or nylon thread, and so we use something called Vectran these days. We also have a stitching head that will allow us to do all the stitching from one side. A traditional sewing machine, you have to have access underneath. The needle sticks through your fabric, and underneath, you have to be able to get to that. With the two needle system, we have a catcher needle and an insertion needle, and one thread goes through, and you'll see a video later about how it marches along. And that means we don't have to have access to the underside of the part. We just need to have a little cavity there for the needles to go into. If you're going to build a very large part and you want to be able to put stitches in the middle of that part, that's really important. You can't do it with a traditional stitching method. So in the bottom corner there is a stiffened panel that we build on Isaac. This doesn't have the resin added yet. It's just stitched together. And if you look close, you can see the white lines along the edges of stiffener. Those are the stitching threads. We're in an enclosure. It's a clean room, but it's not a clean room for the usual purposes of a clean room. We are less concerned about particles in the air than we are about maintaining temperature and humidity. The building we're in, what you don't see is over to the side here, there's a door that opens up big enough to drive trucks in. If it's a day like today, temperature and humidity outside, 90 degrees, very humid, is a very different environment than, say, January when it's 10 or 20 degrees and very dry. The epoxy system we work with is sensitive to temperature and humidity. And we want to be able to build the same part in January and July. And so therefore we got the enclosure so that we can have our own temperature and humidity control system so that we don't have to worry about what's going on elsewhere in the lab. This enclosure is designed so that we can telescope the sections. So the part at the end will move backwards over to the thinner part, so we can use the building crane to get stuff in and out. So it's a very nice setup to be able to do what we need to do for large stuff, but also maintain temperature and humidity while we're building. This is a list of the projects that we've worked. I'm not going to go through these. It's a mix of aircraft and spacecraft projects. Right now, we are focused more on aircraft activities. These are some of the partners, the people we have worked with. Boeing and Spirit, of course, build real airplanes. Generation Orbit is a smaller company that builds launch vehicles, as well as some universities, NASA centers, and of course, Electro Impact and CG Tech, because we're trying to do new and different things with our robot. It's really important to have a good relationship with the companies who build the hardware and the software. So now I'm going to talk about automated fiber placement. And I'm going to play the video and talk about how all this kind of goes together while the video is running. So the first part of this is, I mentioned how we've got an epoxy system. If you think about 5-minute epoxy, it only lasts for 5 minutes. We have a similar type of problem, except we've got 30 days. These spools of material are kept in a freezer until we need them. We bring them out, defrost them, and load them onto the robot. Time almost stands still in the freezer, but as soon as we take them out, we have a problem. It starts going bad. What you saw there is the cutters. If you think about a tape dispenser, pull this out and tear it off. That's how the robot cuts each toe. The part you're seeing now is what we call our mobility demonstration, where you can see how the robot moves. You can see that the head on the robot will spin 360 degrees, which is really convenient when you're actually building a part. So if you get to the end of a row, you can just rotate and come back, and you don't have to keep track of how many times you've spun in each direction. So you can see from here the spools and the take-up reels on the robot, and that's a good image of the infrared heater that we have on the end. This is actually a really cool to see in person. That head weighs about 1,000 pounds, and it stays absolutely stable. That's one of the really nice features of the robot. And from an aircraft perspective, it's really important to be able to do the same thing every time you build it and to be consistent, stable, reliable. And so Isaac does have that capability, which lends credence to when we get results, they're going to be the same each time. As I mentioned, everything is computer controlled from the operator station. Here you can see building a cylinder. That light that you saw there is from the IR heater. And the point of that is to warm the epoxy that's already down there just a little bit so that the next layer will stick. And so it heats it up just enough to make the material stick. After the part is completely built, it will then go into an autoclave where high temperature and high pressure is applied to get to your final part. And for those who are in the room, I've got some parts here that we've built on Isaac that you can come play with. Here you can see example of a spiral. We can program to do, along the length of the cylinder, spirals or other, whatever orientation we're looking for. And you can do patches as well if you only need to put material in a certain part of the cylinder. I mentioned that when we get done building the part in Isaac, we actually take it across the parking lot and put it in the autoclave over in Fab. And so we can get that finished part on site. The part that you see there on the rotator is what we call our complex contour part. It's got concave and convex sections, and that means that we're trying out placing a 1/4 inch wide swath of material over a surface which isn't flat, which guarantees you're going to get wrinkles or buckles in the part. And that's something we need to better understand, because out in the real world, when you have shapes like this, you need to understand whether those defects matter. And it's one of the things that industry up till now has basically just said, we're going to go extra conservative, we'll put down extra material so we don't have to worry about it. But then your plane is heavier, which is the exact opposite of what you're trying to achieve. So some of what we're trying to do at Langley is better understand what those defects are and how they impact the load carrying ability of your final part. Here we're building a part which has a curve like a rainbow shape, arcs, and when you place that, you end up with putting the inner edge of that arc in compression and the outer edge in tension, which means you can get folds and you can get wrinkles. And the wider your toe, the worse it gets, which is why we're using a 1/4 inch toe. But industry wants to go to even wider distances, because that wider swath, because they can build faster. But then unless you're doing a completely flat surface, you've got more defects. So those are the kinds of things we try to look at. When we want to set the head down, we put it in our transfer stand. Very quick process. And then we can go up and pick up a different head. The video doesn't show our stitching head, but I'll use the example that's here, where we can go over and pick up a different head, and then we can go over and use that. Very straightforward process. We have an ultrasonic knife that will cut a pre-programmed path in what we call the green material, the material that we've just placed on the table. And that can be very useful if you're trying to get a shape that isn't, something that's easy to program, or if you want to cut out a circle or something out of your part. And so now I'll go through just a little bit now that I've set the stage. These are the projects we worked. I talked about defects with our complex contour shape. Basically, what we're trying to do is understand the consequence of these wrinkles and these folds. Using NDI, we can pick up FOD. So we're just trying to find what is the consequence of all those defects. And we're working with places like the University of South Carolina to figure out how do you design to avoid those defects. And maybe you've got the same part, but maybe you start building in a different place and you can minimize the amount of defects or the consequence of those defects. Toe steering is when, instead of laying the fiber down straight, we do it in those arcs, but perhaps we do it in a more interesting pattern. And so what we're trying to do is just understand what the limitations are and what we can do. And so again, it's all about the defects, but we're trying to tailor the part to your loading. So if you've got a very complex loading and you want to, say, go around a hole that you know you're going to put into your structure, you want to know, is that going to work? And it depends on the size of the hole and the location and the loading. And those are the kinds of things that we can explore. Another aspect is integral stiffening. What you see here is placing straight fibers, but if you build them up by only placing, say, 1/2 inch wide, 2 toes at a time, you can actually build up a stiffener. If you build your skin and then come in and put your stiffener on top of it, it's going to pop right off. There's nothing holding it there. So that's not a good way to design things. What we can do with integral stiffening is we can place, a layer or two of skin, then come in and put a few plies down that are just that stiffener, and then come in and put another layer that's the whole panel to encapsulate those toes. Now, you can bend the panel, they can't pop up because they're held in place. And so that can be very helpful. That's not something that is typically done. It's something we are exploring to see what the manufacturing restrictions on that are, as well as what the consequences are. The finite element model will tell us how well it will behave, but then we build those panels, we take them over to the lab in the building across the street here, and we find out, do they actually behave the way that we think they're going to? So that's kind of some of the work we're doing now. We also have looked at very thin plies of material. If you want to build fast, you want your toes to be thicker. But if you want to get to optimal structural efficiency, you want the toes that are in the direction that you don't have as much load to be thinner. You never want to build a part that the fibers only go in one direction, because then all you've got in the other direction is epoxy. It will be very weak. It will break. So you always put some fibers in multiple directions, but if you only need a very small amount, maybe you only put in a layer that's half as thick in the 90-degree direction as you're putting in the 0-degree direction. Particularly useful for spacecraft where they are so very sensitive to weight. And speaking of spacecraft, this is an example of looking at lunar lander legs. This is not the methodology that's on in current design scenarios, but it's something we looked at some years ago, where we were trying to say that, in the lunar lander, all the legs, come together up at the top. So you'd like the leg to be a larger diameter. That gives you the better load carrying capability, stiffness, strength versus the amount of load going through it. But you eventually have to bring all these parts together. And so that's what we were looking at here, is placing material so that we could get to bring them all together at a node. But of course, again, that brings in defects. Some of you are familiar with NTF. The National Transonic Facility here does not have a full set of wind tunnel blades. So if something really bad happened in the tunnel, they'd be down for a long time getting new blades built. Unfortunately, we can't build blades quick and easy the way they had suggested. Takes a lot of design work and a lot of trials. And we had a little bit of money one year to actually try doing some of that. And that was what you see here. This blade actually is a representative shape from a Ames wind tunnel blade, where we were trying to work out some of the features that would be needed for an NTF blade. And I brought the part that you see there over. So if you want to come over and look at it after we get done, you can do that. Now, through thickness stitching. So changing gears here, now we want to address the problem of the weakness in the thickness direction. With AFP, all you've got through the thickness is resin. You have to come back in and build in lots of fasteners to keep those layers from separating out in the real world. Needless to say, drilling holes in your structure is not the ideal. I'm at heart a structures person. To me, holes are crack starters. You want to get away from holes. And so that means that you want to find ways to make your structure hold together well without having to go in and putting the holes in. And so through thickness stitching, where we use Vectran threads that we can use to combine your stiffener to your skin, that you can stitch around the edges where you might be subjected to damage from runway stones, hailstones, tool drops, even carts running into the airplane. You know, all of those things are real world situations that will cause damage to your part. With composites, it is possible to have significant damage and not be able to visually see it. Aluminum, you get a dent, you know it's there. Composites aren't that friendly, which is why you have to be really careful and understand the different damage scenarios and damage mechanisms and the consequence of those damage compared to the simpler case of looking at aluminum. Stitching contains that damage. It won't prevent it from happening, but it will mean the damage can't grow. So if you take damage in one place, then that damage might grow as far as the stitch line. It will not grow past that stitch line. And we have demonstrated this in the laboratory and using NDI. And so that was the topic of the Environmental and Responsible Aviation Project some years ago, one of the technology areas explored there. So we were trying to better understand that. This panel was built by Boeing under that project. It was representative of a section of a hybrid wing body or blended wing body center section, which is where people would sit, which means that it's got to be pressurized. It also has to withstand the loading coming into it. So you've got mechanical loading as well as pressurization. And this particular panel is all stitched together. It is fully cured, fully complete, and it has no fasteners in it. And we took this panel, put it in the test article, and it performed like a charm. So we have demonstrated that there is significant potential for the stitching concept. It just means that you have to figure out how to actually build it in an economical manner. To create a stitched part, you start with layers of dry fabric and you place them together into a group, and then you can stitch them together. So basically what you start with is putting together your layers of dry fabric in whatever fiber orientations you want. You run just a couple of threads through it just to hold what we call a stack of material together. And then you take that fabric, you can build up as many stacks as you want, and you run it through the stitching machine. The double-sided system is what I was talking about before, where you have a single needle goes up and down. Great for around the edges of a part. And then we've got the single-sided, which is two needles that go up and down where you can stitch the acreage of the part. The part I showed you on the previous chart is all done using the single-sided system so that it could stitch all those stiffeners onto the skin throughout the panel. And here you can see an example, a cartoon of the different layers of material and how the thread is through the thickness of the part. Typically we use Vectran, but other materials for the stitching thread are possible, particularly if you wanted to go to a very high temperature application. You might want carbon thread, for example, in which case you can solve some of the problems of interlaminar shear and interlaminar tension that you typically get with things like heat shields. This is a little bit more about the double-sided stitching capability. I'm not going to go into the detail here. And this one is the more of double-sided stitching. And here's single-sided stitching. This is the more interesting one because you've got two needles. It's not what you typically do. Then you've got one spool of thread. It goes through the needles, goes down and up and around, and you end up with one side of the part looks like this, and the other side looks like this. And I've got some examples here I can show you. These can be put into complex patterns, and when I get to the video here, you'll see some of the things that we have done there. And so it doesn't go fast, but it will solve so many of your structural problems that there is value in the long run. The other thing is, if you need to add your stiffener to your skin, typically you come in, you drill holes, you put in fasteners. Here you can skip all that stuff. And so you have to think about the big picture of building the part, what's all involved to actually understand the true value of stitch structure. Here you can see the cavity I mentioned, where this is all you need. You need a space underneath to put your needles through rather than needing actual access under here. And then here's are some of the stitch patterns we were doing when we were playing. You know, what can we do here? How tight a radius can we get? Things like that. We have the ability to program this all up on the computer, and we can make modifications directly in the G code that the robot understands. When Boeing built that big panel, everything was done with a touch probe. And so if you want to start at point A and go to point B, took the touch probe, touched it here, touched it there, and that would be how it would create its program. We can actually do real programming into whatever shape we wanted. Using that touch probe approach to think about it, that means you can only go in straight lines. So to get a curve, they would do lots of straight lines. Our system is far superior to that. We can actually do whatever pattern it is we want. Here's an example of some complex shapes. You think about the side of the fuselage, it's curved. That's the kind of area you need to be able to do. And then the other, this is a kind of looking at kind of that wind tunnel blade shape. That's where we're trying to see what can we do here. And so a lot of this is experimentation. This is true, research into figuring out how this could all work. The other advantage, which I have stitch structure, which we can work with is, like I mentioned, you want to build a large part without having to come back in and put in all those holes. That's what's called unitization. So instead of having lots of little pieces that you end up putting together, you build one big part, like that panel that you saw on the earlier chart. That can save a lot of time, but it also means that you've got a very large part that you're moving around, and that if something does go wrong, you've better be able to make a repair to it. And so those are the kinds of advantages, things you have to think about when you're actually building parts. We're trying to increase the speed of assembly. Again, if the farther we can get along in technology development, the more likely industry is to adopt this to put on their next airplane. And so some of the things that we look at is trying to be able to speed up the process. And I'll talk about that more when I get to the video. And back to the wind tunnel blade. We tried with AFP first and decided that really wasn't an effective way to build new wind tunnel blades. The problem with the way they were built back in the 1980s and 90s was that it was all done by hand. And great, go to an automated system. The problem is, even with an automated system, they had lots of little pieces. And that means that no matter what you do, putting together lots of little pieces is going to be time consuming. And so what we suggested was, what about stitching with its unitization? And if you think about how these, you can see here, think about taking a piece of paper and folding it like origami into whatever shape you want. That's what we can do here. We can take that sheet of dry carbon fabric and stitch it one way, fold it, stitch it a different way, and then you can get to whichever shape you're looking for. And so you've actually got continuous threads, continuous carbon fibers through your part, and it's all put together, and you potentially could build something this complex, including the airfoil, the platform, all the pieces here in just 2 or 3 big parts, and then put them in an oven to cure them. And that was what we were hoping, that the NTF folks would find enough money to support us. Sadly, that did not happen. But we learned a lot from this activity. And here you can see more of coming out of that. We were looking at the airfoil. Part of that, if you saw up there, there's the section at the bottom where you want to have fibers that are continuous around here. The wind tunnel hub, you would have a pin that runs through here. And so you want high strength through here. You don't want it to break here. And so one of the things we were looking at was how would we stitch that? Well, we rigged up something and tried it out and see, oh yeah, we can actually do that. And so that's some of the things that we're trying to do, and push the limits and understand what we can do. The other thing that we looked at was trying to do stitching better in a more compact manner. That big cavity you saw in the earlier chart underneath there allows the fabric to sag, which means you have to stretch it really tight, or you have to put a layer of fiberglass underneath to keep it from sagging. Well, we found a way to put that material over a very small cavity by rotating the head. And instead of stitching with 1/4 inch wide part, we can stitch in just millimeters wide. And so we have a much smaller cavity, which means you've got a much tighter seam. Is that the right thing for all applications? No, but there are places where that could be very useful. And so those are the kinds of things that we do. We call this side slip stitching. And now I will show you some stitching in action. This is with the single needle system. This just, we like to show this because yes, we can do this all programmed up as opposed to the way Boeing used to do it. So, we like to brag about that. But this can show you, a sine wave or a circle or whatever it is we're trying to do. This is the more interesting part because this is the double needle system. And this is using a larger cavity underneath, but it's a curved part and everything's programmed. Here we're going around a circle. If you think about sitting on the airplane and the window belt, if you could stitch around each of those windows, then that's less material you might need to have around those windows, because normally you would have to put in doublers because you're going to have to drill holes in there because you've got to put a window frame and all. By putting the stitching in, perhaps you can avoid putting in those doublers because now your holes can be contained, and even if damage does start at the hole, it can't go anywhere. And so that's where we're trying to develop technology with particular applications in mind. And so it's the window, it might be an access door on your wing. There's lots of potential for that activity. Here, if you think about having your skin and the stiffener would be underneath this part. And if you'll notice here, what we'll do is what's just called stiffener jumping, where what we're trying to do is not have to stop stitching, move the robot to the beginning of the next location and go forward, but rather let the thread just spool out enough and then keep going. And so this could all be programmed in so that on the other side, we don't have to worry about where the stiffener locations are as far as doing the stitching here. And so again, it's not what you need for everything, but it has particular value. And then here you can see just another view of stitching over a complex shape. And that's the end of that part. We also have, we call our development head, which is for new capabilities. If somebody came in and said, hey, I want to try this out, we would negotiate with them. Okay, what does it involve? How can we make this work? And we have the opportunity to say, okay, we've got a blank head here. Power, air, data, how could we make this work? We are also looking to be able to look at thermoplastics instead of just epoxies. The problem with thermoplastics is they require much more heater. So that IR heater that gave the little light out when we were replacing the epoxy material can't get to a high enough heat. You have to go to a laser. And that laser, to put out enough heat, is a very dangerous laser. And so, yes, we can get the head modified to be able to handle that laser, but now we have to make that clean room safe. And you saw the earlier pictures where all that's between the head and the operators is a fence to keep people from going back and forth. That's not going to stop a laser. And so the big part of the problem here is we need to be able to, make the clean room safe for laser capability. We're working on that, but that's going to be a couple years before we have that in place. And so I'm not going to read through the summary kind of stuff. Isaac has contributed both AFP work and through thickness stitching work to a variety of projects, looking at a whole range of different aircraft and spacecraft applications, development activities. And we are still open for business. And if any of you take this information back to the branches you're working in, and you think of an area where you think stitching might be applicable, or you think automated fiber placement might be applicable, we are open to discussions. And that's it. So thank you.